Good day, good morning. We're back with ESSI lecture series. It's Monday, July 6th, before noon, 11:20 California time. We're only back in California. My name is Boris Jeremic, and today with me are Dr. Han Yang.
Hello.
And Mr. Heshen Wang, who...
Hi.
Yes, hello. Mr. Heshen Wang, who will talk today about DRM developing motions from surface records for input into DRM into Real-ESSI models. So,
Yep.
Heshen, let's start your video.
Okay.
Share your screen, and then let's see how that. Let's see if we can get. So again, I get this full screen. I do not know why. Exit full screen. Okay. Try the option where you have. Try the upper right option. See if we can see the.
You mean my upper right option?
Well, we are seeing your screen, so try upper right. See if you can show our videos on the side.
Yeah, on my screen I can see all your faces on my side. Yeah, but I think
okay.
the recording is on your computer, so yeah.
So maybe I should. Anyway, okay. Don't worry too much about it.
Yeah.
Okay, don't worry. Just go ahead, and then we'll go back and forth and comment. Yes, go ahead, please.
Yeah. Okay. Yeah. So yeah, as Professor introduced, yeah, today we're going to talk about the development of 1C, 2 times 1C, and 3 times 1C DRM motions from the surface seismic records. So yeah, to begin with,
can I just say a word? So 1C, 2C, 3C. We used to call this 1D, 2D, 3D, but some French colleagues of mine actually insist on calling this 1C, 2C, 3C, and I think it's very, very appropriate. You know, 1D, 2D, 3D would be for dimensions of the model, but these are components. You're talking about components of motion. So if you input SV wave or SVH wave, it's really a one component wave. You can also do two shaking, horizontal shaking. That would be 2C or 2 times 1C, in fact. And you can also introduce motions as 3 times 1C, in which case you're really doing one SV wave in the one direction, SV wave in the other direction, and P wave in the other direction. And that's actually not quite right, but we'll talk about it in the next lecture when we actually talk about 3D motion. So that's the reason we call these 1C, 2 times 1C, and 3 times 1C. Please go ahead.
Yes. So as Professor already explained that, so this 1C is a one component motion, 2 times 1C is 2 times one component motion. Essentially, you have a one component motion in 2 directions. Yeah, and the 3 times 1 component is 1C motion, which we call 3 times 1C motion. Is you essentially have a one component motion at the 3 different directions, 2 horizontal direction and 1 vertical direction. But for each of these components, they are all assumed to be uniform, linear elastic, and a vertical wave propagation of one component seismic motion. And you might have a shear wave in 1 or 2 horizontal directions, and you have P wave in the vertical direction. So this is the underlying the modeling assumption. And today, our goal is to develop a one component, 2 times 1 component, or 3 times 1 component free field seismic motion for DRM input from the seismic records. And in order to do this, you're going to need the 3 information. First of all, you need the information about your DRM. Right? You need to specify the geometry of the DRM, the location of the DRM, and the boundary or exterior node as the DRM layer. And also, you need your input seismic records. That can be 1 component, or 2 times 1 component, or 3 times 1 component. And also, a very important point is you need your engineering side characteristics, because we're going to do a convolution or deconvolution, depends on where your seismic records is located. Yeah. Yes, Professor.
So just a note. So DRM, domain reduction method by Jacobo Bielak. So we need, remember, it's a single layer of elements that surrounds your model, your solid structure interaction model, and that single layer of elements. You do this, of course, during mesh generation, during development of the model, but you need to have that information saved, and Heshen is going to show in what format we save this in HDF5 format. But so you need to specify geometry of the layer, locations, boundary and exterior nodes, and there's a trick, we'll mention it when you have actually, let's say, 27 node bricks, which ones are boundary, which ones are exterior nodes. So the DRM information really is the information about geometry and all the numbering of all those elements and nodes that belong to those elements in that single layer of elements that surrounds your soil structure
Yeah,
model. Yes, go ahead.
yeah. Yeah. So yeah. For those who are interested in DRM, we have a previous professor has a theoretical lecture on the
Yeah.
method of the domain reduction method. So you can go back to these lectures to know the theoretical details of the DRM. So in order to use the DRM method, the most important thing is you need to have a free field motion at all these DRM nodes, and they can be either boundary nodes or exterior nodes. Yeah. And this lecture is showing you how to generate these free field motions from surface records. And so we will start with the first part is how to specify the information of the DRM layer. So in the Real-ESSI modeling and simulation system, we're going to specify this DRM information through a HDF5 format file. And essentially there is like 6 different data sets in your in your input HDF5. For example, the first one, you might want to specify the DRM nodes dataset. Essentially, that will contain a 1D column vector of integers of size n, where n is your total number of DRM nodes. And these n integers will specify all the node IDs in your Real-ESSI modeling of your DRM nodes. And we suggest you to first put the boundary node, which is the node that directly connected with the inner soil or inner soil structure system, and then followed by the DRM exterior node ID, essentially the node that is the outside of the boundary node.
Just a note, so you can do this by hand by using MATLAB or Python, but it can also be done automatically by GMEasy. But it's a good thing to know what goes inside and why it goes inside. Yes, go ahead, please.
Yeah, yes. And then you need another data set, which is the elements data set. This is again a 1D column of vector of integers of size m, where m is your total number of DRM elements. And this data set will provide all the element IDs of your DRM layer. Because in the Real-ESSI program, we're going to apply this effective DRM force to these elements. Yeah. And then the third one you need is the coordinate data set. And that is also a 1D column vector of doubles of size 3 times n, because for each DRM node, you're going to specify 3 coordinates x, y, and z. And the order of these coordinates is corresponding to the node ordering in the DRM node dataset that you already previously defined. And so this node is also very important, because a different node will corresponding to different location of your ground depths, and they will used to be generate the motions at that depth. So this is also very important. And also you need to specify the coordinate according to the order of different DRM nodes as you defined in this DRM node dataset. And then you have these two data set, which is the number of boundary node and the number of exterior node. This is just a single integer in each of this data set group, and we'll specify how many numbers of boundary node and how many number of the exterior node in your DRM model. As Professor mentioned that, so if you have a 27 node break, so essentially you will have only a single layer of the boundary node, but you will have 2 layers in the middle part and also the exterior part, as they are all both counted as the exterior nodes. Yeah.
So note, if you have a 27 node brick, remember you have 27 nodes. This one face that is a boundary face is going to have 9 nodes. Yes. And then the other side, so the middle plane, which also has nodes, 27 node brick, and the outside is going to actually have 18 nodes. So it's very important to. There are some questions that I got from users previously where they forgot to put this middle layer. So the inside 9 nodes and then 18 nodes are second layer and third layer outside.
Yes, that's true. So in that case, your exterior node will be like double size of the boundary node. Yeah. Yeah. And then the final data set you need to provide is such a set called is boundary node data set. So this is the data set that has the same dimension of the DRM nodes data set, and also of size n. So this is in this data set, essentially it contains a 1D column vector of Boolean, essentially 0 or 1s. So if this is 1, that means corresponding DRM node is a boundary node. And if it's 0, that means corresponding DRM node is an exterior node. So this vector is this data set is very important because the effective earthquake force coming from the DRM formulation, if you go back to our previous theoretical lectures, are different for boundary nodes and DRM nodes. So for boundary node and exterior node. So it's very important to specify, each node you define in your DRM nodes dataset, whether they are boundary node or exterior node. So if you organize your DRM node dataset with the format that you first put the boundary node and then you put the exterior node, then in your east boundary node dataset, the first part is just going to be ones, and then the rest part is going to be zeros. And it's also a good check for you to see whether these numbers are matched with the number of boundary node and number of exterior node in this other two data sets that you provided before. And so once you finish the definition of this DRM input part, so the second component you also need to provide is the seismic records. So for each component of the seismic for each component of the one component motion, you need to provide their time series acceleration and time series displacement. And we in Real-ESSI we organize them into just a simple plain text files, and they follow the two-column format. The first column is time, and the second column is corresponding acceleration or displacement ordinate. And the very important point is that you need to make sure your seismic records is baseline corrected. This is especially important if you have some for the displacement signal. So if your seismic signal is not baseline corrected, they might have generated some non-zero starting point, well, after you do the deconvolution, they might have some non-zero starting motions, and that will create problems when you do the FEM modeling. Yes, Professor.
A note, because these are surface records that are going to be deconvoluted, and then they're going to be propagated back using DRM, using Real-ESSI. DRM, domain reduction method, is a very physics-based method. It's very sensitive to, how shall I put it, to wrong motions, to wrong waves. So, I mean, you can't just put any wave because it's going to create. So this is important to actually have these properly done, to have a corresponding displacements and accelerations waves that are propagating, in this case, as one component waves, P waves or SH or SV waves, but they have to be properly baseline corrected, and they have to be proper physics-based waves, because DRM is going to be very sensitive if the wave is not physics-based, then you get all sorts of high frequencies and that are not physical, essentially. Yes, go ahead, please.
Yes, that's true. Yeah. And then the third component, as we mentioned before, is your engineering side characteristics. So to define the engineering side in Real-ESSI, we also going to use a plain text form, plain text, and this plain text file going to contain 4 columns. And each row of this column is defined a single layer, the property of single layer. So the first column is the velocity. So if you are doing a one component, horizontal component, you need to specify the shear wave velocity for the first column. But if you are doing the vertical direction, which is the P wave, you need to specify the P wave velocity for the first column. And then the second column is the ground density of that layer. And then the third column is the damping for the layer. And the last column is the layer thickness. And we always assume that the last layer in this file, specify this file, is an infinite half space. So you don't need to specify the thickness for the last layer. And for now, in this file, you do not need to specify any units, but whatever units you need to use is going to be specified in the DSL commands, which I will introduce you in the later part. So yes, Professor.
So just a note, first of all, you can always put these comments, and it's very useful to put as many comments as you want. I mean, of course, this file is going to work fine if you just put these numbers, but comments are really important. As Session was saying, units, we don't specify units in this file, but we're going to specify in the DSL, the Real-ESSI input. And remember, we always use units, so it's important to follow through with appropriate units. I mean, you can mix them up. Everything is going to be converted to SI system inside the system, but you won't see that. But in this case, you will provide input units later on. One more thing. The damping here is because this is going to be used for deconvolution using essentially linear elastic, equivalent linear elastic wave propagation backward, and so that's the damping part that is required here. Yes, go ahead.
Yeah. So actually, this damping is a violent damping. So it's a frequency independent. So it's the same damping ratio for all the frequency range. Yeah, it's not like the relay damping or Coulomb damping that you might familiar in the structural dynamics. Yeah. And also you can see we have a big note here. That means you cannot you need to be very careful with the ground profile that you are specifying here, because this ground profile should be kept the same as the ground profile for your DRM layer and for your inner soil layer when you used in your wave propagation in the FEM modeling. Yeah. So if they are not consistent, the DRM will not work and will generate a lot of local effects. Yeah. Yeah.
So we had issues with some users that it's by mistake, essentially by oversight, they would have one profile here and then different profile in the actual propagation. So again, this profile is going to create a wave field, a one component wave field, SVSH or P wave field. And that wave field has to be compatible with what you're going to propagate back through Real-ESSI. And if they're not compatible, you get some strange results. So you have to be compatible. You have to be consistent in making sure that the profile that you use to develop wave field is the same as the profile that's going to be used to propagate the waves back. Go ahead,
yes,
please.
that's true. Yeah. So then if you have all these three components prepared ready, then we can go to the, you can define the one component seismic wave field in Real-ESSI with this DSL command. So as you can see here, you have a bunch of units you need to specify. This is the unit that we were mentioning before when you define the profile. And so I'm showing you an example that how I define the seismic wave field. So first of all, you need to define the tag for your wave field. So if you have multiple components, you need to define the multiple tags. You might define one horizontal component at wave field number 1. If you have another horizontal direction, you need to have wave field number 2, and you might want to define your vertical direction at wave field number 3. But for each of these wave field, you both need the specify their acceleration, the file that you prepared before, and their units, the displacement file, and also the displacement units. And there is a very important part here is called compensation time. And when you do the deconvolution, it's always good to add some compensation, because as you can imagine, when the wave propagation, the wave in the depth is always starting earlier from the surface records. So if your surface records is directly starting from the 0 seconds, then as you can imagine, when you do the deconvolution, your motion at the depth will have a non-zero starting point. So that is will create problems for when you do the finite element modeling. So we will suggest you to add enough amount of compensation time. Essentially, we will padding a bunch of zeros at the beginning and ending of your original input seismic signal, and then we do the deconvolution. So then you need, yes.
No. So essentially, what you're doing really, you're essentially predicting how fast or how early you should start so that the wave actually has time to propagate. So depending on the shear wave velocity or P wave velocity, and depending on the depth of your model, you can make an estimate here. So 2, 3, 4, 5 seconds. It doesn't hurt that you're just adding zeros, but it helps really, because then you get the proper waves that are starting from 0, and then they slowly propagate and start exciting the system, the surface system. Yes, Han, please.
Yeah. Just a quick additional note from experience by working with this command, that you really want your original acceleration and displacement record of your earthquake to be complete. What do I mean by that? Like, you want the motion to go to 0 in your original record. Like, you really want it to die down. Otherwise, if you have an incomplete, then when you like, let's say at the end you have some non-zero value, and then you added a compensation time, which is adding a number of zeros, that will create all kind of numerical problems. So you really want your original earthquake record to be complete and really die down to 0 at the end of the motion.
Yes, and if I may add, I mean, usually those records still do have some things, still have some small motions at the end, but you can kill those and put some padding toward the end or at the end with number of zeros, so they all end up with 0. So motions start with 0, padding time, compensation time, they excite the system, and then they die down, and you put some seconds before and after. Yes.
Yeah, that's true. Yeah, that's true. Yeah, that's also the reason why we ask you to baseline correct your motion, because once you
Yes.
baseline correct it, your acceleration and displacement will go die down to zero, and then you can safely pad in these zeros, because otherwise it will create some high frequency component, which is
Yes.
unrealistic. And then the next parameter, you're going to specify your monitoring location. You can either specify either to be a within soil layer or outcrop motion. So if you want to just have a surface records, then you should specify the within soil layer. And then you need to specify your soil profile that you defined before, and also a bunch of units associated with this soil profile. Yes. So this is a DSL command to generate such a 1D seismic wave field. You might have a multiple, seismic wave field. As I mentioned before, you might have wave field number 2 and number 3. So once you properly define this seismic wave field, then we have a additional set of DSL commands that will enable you to generate the DRM input motion from this defined seismic wave field. And you can either to be one component motion. Essentially, you only need to specify one wave field, and you can also, if you want to define a 2 times 160, two component, two horizontal components, you need to specify two wave field, and also you need to specify corresponding direction. For example, I can be wave field number 1 here and the direction ux, and the wave field number 2 for direction uy. And also, if you want to specify the 3 times 1 component, obviously you need to provide 3 different wave field component at 3 different directions. And yeah, and also most important thing is you need to specify your HDF5 name as a string input. So I will show you an example here. So here is the example. The first example, the upper part here, I'm generated the DRM input from the one component seismic wave field number 1. And also this will be applied in the x direction. So instead, this is only a 1D motion in the x direction, and it will write these motions into this specified DRM input. So this DRM input is written or generated by GMEZ according to the format that we introduced before. And the down part here, I'm generating the DRM motion from a three times 1 component seismic motion. Wave field number 1 for x direction, wave field number 2 for y direction, wave field number 3 for the z direction. And also I specify them to generate the motion into such a HDF5 input. Yes, Professor.
And that HDF5 file is the same file where you specified all the information about the DRM and so on. So it's going to take that file, it's going to add all these motions, and it's going to save it again on the disk.
Yeah, so once you execute this DSL commands, you can see, so this is a file that you originally specified to the input to the Real-ESSI. So here you have only all this geometric information about the DRM. And after you successfully do the define the wave field and do the deconvolution, you should be able to see the additional 3 components data set is generated. Number 1 is the acceleration, number 2 is the displacement for those DRM nodes, and also the time vector. Yeah, and with all these 3 components, the Real-ESSI can take this information and generate the effective earthquake force and do the earthquake soil structure interaction simulation. So the final additional note would be, it's always good to do a free field verification check for this one component or 3 times 1 component generation of seismic waves. When you do once you have your DRM file generated, you can do a simple FEM model, which is the free field model, has the same SARE and soil profile. When you do the deconvolution, the soil profile you specified before, you do the FEM wave propagation using this DRM input file, and you can see whether at the surface of this DRM from this FEM wave propagation can match the original seismic input, seismic signal that you are input. Yeah. And if you get the fully match, that means you are good. And then you can do some nonlinear side response or nonlinear earthquake soil structure interaction analysis. Yes. So with that, you can look for more information into our reference, look into lecture notes, and again, we will give thanks to our collaborators, this funding resource in the collaboration with these funding resources, and also you can check out our website for more information. Yeah, thank you for your attention.
Thank you very much. If you get out of the screen sharing
yes.
option, Well, thank you very much. So this is, we'll get back to this. We'll talk more about inputs with the plane waves and whatnot, but this was very useful because this specifies how to get the motions that are specified at the surface or at some depth, how to propagate them using deconvolution and then convolution back to the system. This is really what practice currently uses a lot. So anyway, thank you for that, and we'll continue with our next lecture in a day or two.
Okay.
I'll stop recording right now.